Let's move up to layer 3 now and see what's going on at the network layer. What is the network layer responsible for? You might remember that the data link layer was responsible for physical addressing like a MAC address. Well, the network layer is responsible for logical addressing. And in our environment, the logical addressing we're going to be using is probably IP, the Internet Protocol, maybe IP version 4, maybe IP version 6, but it's probably going to be IP. But the OSI model was written back in the day where it wasn't just IP that was really popular. We had other things that we might want to route as well. I remember when I used to work at a local university, we routed IP traffic, IPX traffic, AppleTalk traffic. Each of those routable protocols had their own logical addressing. So instead of physical addressing, at the network layer we have logical addressing, such as an IP address. Layer 3 is also concerned with switching, and this might seem odd because switching is normally thought of as a data link layer concept. We have Ethernet switches, after all, at the data link layer. Here, though, at the network layer, when we talk about switching, we're talking about how we're going to send a packet from one device to another device. There are three basic approaches: packet switching, circuit switching, and message switching. The one we're mainly going to focus on is packet switching. With packet switching, data is divided into packets, and these packets contain a header. And this header says, where did the packet come from? What's the logical address? Where's the packet destined? What's the destination logical address? And a router, a hardware component that lives at layer 3, that can examine the packet and make a forwarding decision for that packet. It's going to this logical address. That logical address is via this next hop router, and this router operating at layer 3 can make a decision to forward the packet on to a specific next hop router. There's also circuit switching. With circuit switching, we bring up a circuit on demand. It's not up all the time. Think of it as placing a phone call from a traditional landline, maybe in your home. You pick up the phone and you dial a number, and when you dial that number, a circuit is brought up between you and the person you're calling. And then when you hang up, the circuit is then torn down. Finally, there's message switching. With message switching, our data stream is broken into messages. And like a packet switch, there is a destination address, and that's going to determine how we route the packet, but it's not necessarily real time. It's more of a store and forward approach. It's more like email, where it might be stored on the next top device and then sent to the next device and then stored there for a time and then sent again. So again, this is more of a store and forward approach. We don't see that much. Primarily, we're going to be focused on packet switching. Something else that a router is concerned with at layer 3 is route discovery and selection. When a router is interrogating the header of an IP packet, and it's trying to determine, how do I get to this destination address based on the networks that I'm aware of, we need to ask ourselves, how did the router become aware of those routes? There are some different ways. Maybe the router is physically connected to a network. If a router is connected to network 10.1.1.0 with a 24-bit subnet mask, which we'll be defining later, then it knows to get to that network, we just have to send a packet out of that interface that belongs to that network. So we could have a directly connected route. We could, as an administrator, go in and administratively add a route. We could statically add a route to say, to go to this network, go out of this interface, or go to this next hop IP address. Or we might have dynamic routing protocols. With dynamic routes, we can have a routing protocol such as OSPF, Open Shortest Path First, EIGRP, Enhanced Interior Gateway Routing Protocol, RIP, the Routing Information Protocol, and those are just a few examples. But we can have some protocol that is going to advertise between routers information about how to get to different networks. And because it's dynamic, if one network becomes unavailable off of one of our neighboring routers, we can know about that. We can remove it from our routing table because it's no longer reachable by that neighboring router. Layer 3 is also concerned with connection services, and here we're talking about things like flow control. If the sender is sending too rapidly, we can ask it to slow down. If packets get out of order, the network layer is capable of reordering packets and putting things back in the correct order. And we were mentioning that a hardware device that lives at the network layer is a router. Let's now take a look at an actual router and consider, how does a router make its routing decisions?
A common device that we see at the network layer, layer 3 of the OSI model, is a router. This is a smaller, older Cisco router, but it's got a few interfaces. I've got a couple of serial interfaces, I've got an Ethernet interface, and the way a router is drawn in a topology, it looks a lot like a hockey puck, like you see here. This is a router, and you'll notice that I have the router connecting out to a couple of switches, connecting to another router, which connects to yet another switch. We've got some end devices connected as well. Let's add one thing to this. Let's add a connection out to the internet. I'll draw a cloud, and we'll make this a WAN connection, the lightning bolt connection. And we'll say that is the internet. What we want to talk about here is how does this router specifically learn about all of the different networks to which it's attached or which it can reach. You see that I've got one network, and if you're not yet familiar with network addressing, that's coming up in a later module when we get into IP addressing. And you might want to come back and revisit this video at that time as a refresher. But we've got different network address spaces, different network addresses that can be learned by the router. And in devices, they have an address in that network address space. For example, I've got a laptop and it has an address of 10.1.1.2. The /24, that represents something that we'll learn about later called a subnet mask. But the point is, this device at 10.1.1.2, it's in a different network than this server, which has an IP address of 172.16.1.2. It's in a different network than this PC with an IP address of 192.168.1.2. And then we have thousands upon thousands of addresses out here on the internet. How does the router know about all this stuff? Well, there are different ways that a router can populate its routing table. Here we have a basic routing table, and we're listing the source, in other words, from where did the router learn this information, the interface, off of which interface should the router send a packet to get to a destination network, and what is that network? Let's take a look at what the router knows about. First of all, it is directly connected to some of these networks. The router is directly connected to the 10.1.1.0/24 network. When we learn about IP addressing and subnet masks, we're going to see that the network address is actually 10.1.1.0/24, and that's available off of interface 1. Now, in the real world, that would be something like fast Ethernet 0/1. But just for simplicity right now, let's say this is interface 1. How did we learn it? We learned it because we were directly connected. I'll put in a C for connected. What about this network? This network is going to be 192.168.1.0/24. Let's write that down. 192.168.1.0/24. It's available off of interface 3, and it's directly connected. Now, when I say it's directly connected, you might say, hold on, it's not directly connected. We have a switch in the middle. Well, a switch, remember that a switch does not separate broadcast domains. In other words, it doesn't separate network address spaces. Everything off of this router, all the way through this switch, that's part of the same network address space. So this is connected. However, here we have a router. A router does break apart network address spaces. So we've got this network of 172.16.1.0/24. It is not directly connected. How did we learn about this network? It's available via a different router. We could have statically configured it. We could have gone in and administratively said, to get to this network, we should send packets to an X-top address of this router's IP address. Or we could have been running a routing protocol, such as OSPF, EIGRP, RIP. We could have dynamically learned about it. Let's pretend that's what we did. Let's pretend that we learned this network, which is available off of interface 2. We learned it via OSPF as our routing protocol. And we have one other network we've not yet considered. Let's say that this is interface 4 getting us out to the internet. The internet has hundreds of thousands of routes. Do we want our router to know about each of those individual routes? Maybe not. Now, some routers might, but maybe not. What we could do instead is say, I want to create a default route. I'm going to create a static default route to say, if I'm trying to reach a network, and it's not any of these networks, it's none that I'm local to, it must be out on the internet. As a default route, go out to the internet, go out of interface 4. So we could add a static address. The static network address to 0.0.0.0/0, that's a default address. In other words, if it's none of these, go here. We're going to go out of interface 4. How did the router know about this? We told it. In other words, it's a static address. To sum up, at layer 3 of the OSI model, a common device that we have is a router. A router makes forwarding decisions based on logical addresses. The router can learn about networks because they're connected to the router. We statically configure them in the router, or maybe the router dynamically learns these addresses.